Welcome to EGME-331 Solid Mechanics Prerequisite video series. In this video, we'll be reviewing the shear force diagram. So what is shear force? Shear force or shearing forces occur when a perpendicular force is applied to a static material. It's most commonly used in the case of beams. Think of cutting an apple with a knife. Imagine that the beam is an apple and a point load is a knife. As the knife applies a downward force, it cuts or shears the apple. These shear forces occur along with numerous points of a beam, and it is important to determine where these shears are at the greatest point, as this may be where a beam fails or where the failure occurs. Now, shear force diagram is a graphical representation of the variation of the shearing force on a portion or the entire length of a beam or a frame. So, shear force diagram, SFD in short, is one which shows the variation in shear force along the length of the beam. Coming to the sign convention for shear force, a positive internal shear force causes a clockwise rotation of the beam segment. That is, it pushes a left-facing cross-section upward or a right-facing cross-section downward. So as a sign convention for the shear force diagram, the SFD is drawn above or below the X central axis of the structure, but it must be indicated if it is a positive or a negative shear force. Let's take a look at the shear force diagram plotting procedure with the help of an example. First step is to determine the support reactions. Then we specify the beam sections, the origin, left end to the between each discrete load, the force or the moment. Now shear force is indicated by the letter V. So be sure that the shear force is showing acting in the positive sense. Then the next step is to sum the forces vertically to determine the shear force V. So let's consider drawing the shear force diagram for the cantilever beam shown here that supports a concentrated load of 5 pounds at the free end, 3 feet from the wall. The first step here is to draw a free body diagram of the structure. Then we need to calculate the reaction forces. To calculate the reaction forces, we use the equilibrium equations, and this may not be needed to do if you are choosing a cantilever beam and using the free side of the cantilever for the free body diagram. Then compute the reaction forces at the support. Since the support at B is fixed in this example, there will be 3 reactions at the support, namely at the support B, which are B sub y, B sub x, and M sub b, which is the moment. Applying the conditions of equilibrium, we get the equilibrium equations as shown here. The next step here is to find the internal forces, or rather add the internal forces. For this, make a cut and add the internal forces, the normal force N and the shear force V, using the positive sign convention. Depending on the number of loads, we may need multiple cuts. In this case, only one cut is needed because there is only one load and that is added at the end. If it were added in the middle, there would be 2 sections to consider, and the value of X would be ranging from 0 to 3 feet. The next step is to find the shear force equation. To find the shear force equation, we need to understand the distance from the origin of the reaction for each cut. Here X is the distance from the free end of the cantilever to the cut. The shear force at that section is due to the applied load. So using the equilibrium equation, we can get sigma F sub y would be equal to negative 5 pounds minus V, or V would be equal to negative 5 pounds. And the negative sign here indicates that the shear force acts in the opposite direction. The constant number of shear means that it doesn't change or vary by X. So if there were a distributed load, X would be part of the equation. In this case, it's a constant. As I mentioned, the negative sign indicates the shear actually goes the opposite direction. This is due to the fact that the sign convention, as we just saw earlier, states that the downward transverse force on the left of the section under consideration will cause a negative shear force on that particular section. The next step is to plot the equations on a shear force diagram. Now that the shear force is a constant, it must be of same magnitude at any point along the beam. As a convention, the shear force diagram is plotted above or below the line corresponding to the neutral axis of the beam. But a plus sign must be indicated if it is a positive shear force, and a minus sign should be indicated if it is a negative shear force. A way to check the answer is to ensure that the reaction force brings the problem back to zero. That means the shear force is -5 until the last moment, and when the reaction force is plus 5 pounds, the total brings the force to zero, which means that the area under the shear force diagram above the x-axis should be equal to the area between the x-axis and the bottom side of the shear force diagram. That means the line below the x-axis. That means the net area should be equal to zero. Also, any point where the shear force diagram crosses the x-axis will be a max or minimum bending moment. The bending moment will be discussed in another video. The shear force diagram should always equal to zero at both the ends. Lastly, if somebody asks you for the shear force formula, that's simply just the sum of the vertical forces should be equal to zero.